In March 2024, physicists at CERN recorded something that shouldn't exist. During a routine collision run at 13.6 tera-electron-volts, detectors picked up a decay pattern that violates a symmetry the universe has obeyed for 13.8 billion years. The particle involved was the Higgs boson, and the data showed it breaking a conservation law we thought was absolute. The team ran the sequence 847 times. Every single result came back identical. This wasn't noise, wasn't error, wasn't a calibration fault. The numbers were clean, repeatable, and completely impossible under the standard model of particle physics. What makes this discovery so unsettling isn't just that our equations are wrong. It's that the violation appeared suddenly, in a particle we've studied for 12 years without incident. Something about reality's fundamental rule set has changed, or we've finally pushed hard enough to see a crack that was always there. To understand what CERN found, we need to go back to where it all started, a machine built to answer one question that would end up asking 1,000 more. The machine, the Large Hadron Collider, sits 100 meters beneath the border of France and Switzerland, a ring of superconducting magnets stretching 27 kilometers around. Inside that tunnel, protons accelerate to 99.9999991% the speed of light, circling the ring 11,245 times per second. When they collide, the impact recreates conditions that haven't existed since 10 picoseconds after the Big Bang. The machine operates at 1.9 Kelvin, colder than the cosmic microwave background of outer space. 1,232 dipole magnets generate fields of 8.3 Tesla, 200,000 times stronger than Earth's magnetic field, keeping the beam on course. 4 massive detectors, named Atlas, CMS, Alice, and LHCb, record the debris from 40 million collisions every second. Each detector weighs thousands of tons and measures particles down to scales where quantum uncertainty blurs the line between existence and probability. Building it took 10,000 scientists from 100 countries and a budget of $4.75 billion. The data output in a single year exceeds the entire contents of the Library of Congress by a factor of 50. The machine was designed to find one particle, and when it did, the celebration lasted exactly 3 years. The Higgs discovery. On July 4, 2012, CERN announced the discovery of a new particle with a mass of 125 giga-electronvolts. The signatures matched predictions made 48 years earlier by Peter Higgs and François Englert. This was the Higgs boson, the quantum excitation of the field that permeates all of space and gives mass to every fundamental particle. Without the Higgs field, electrons would travel at light speed and atoms couldn't form. Matter as we know it wouldn't exist. The discovery confirmed the final missing piece of the standard model, a framework that had predicted particle behavior with staggering accuracy since the 1970s. Higgs and Englert received the Nobel Prize in 2013. The detection rate was tiny, roughly 1 Higgs boson produced for every 10 billion collisions, and it decayed in 1.56 times 10⁻22 seconds. But the statistical significance hit 5 sigma, meaning the probability of error was less than 1 in 3.5 million. Physicists had found the particle that makes the universe possible, and every test over the next decade matched theory perfectly. Physicists thought they'd closed the book on fundamental physics, but then the Higgs itself started behaving strangely. The first anomaly. In 2016, a team at Fermilab measured the mass of the W boson, a particle that carries the weak nuclear force. The number came back 0.1% heavier than the standard model predicted. That sounds trivial, but in particle physics, 0.1% is the difference between a working universe and one that shouldn't exist. Then came the muon G2 experiment. Muons are heavier cousins of electrons, and when you spin them in a magnetic field, theory tells you exactly how fast they should wobble. Except they didn't. The wobble was off by 4.2 sigma, a deviation so large that if it held, It meant unknown particles were tugging on the muon from outside the standard model. Most physicists filed it under needs more data, measurement error, calibration drift, statistical fluctuation, but a handful of researchers quietly began checking whether the Higgs field itself might be unstable. The discrepancies were small, scattered across different experiments, easy to ignore, except they all pointed in the same direction. Those whispers stayed quiet for nearly a decade until CERN's 2024 upgrade brought something into focus that nobody was prepared to see. The upgrade, the High-Luminosity LHC, came online in March 2024 after 4 years of construction and $1.04 billion in upgrades. The machine now smashes 10 times more protons together per second than the original design, generating collision data at a rate that would have been unthinkable a decade ago. New superconducting magnets focus the beams tighter. New detectors catch particles that live for 10⁻23 seconds, particles that used to vanish before anything could register them. The goal was to hunt for dark matter candidates and study rare Higgs decays with enough precision to see if the standard model had cracks. CERN expected to spend years combing through petabytes of data, isolating signal from noise, building statistical confidence one decimal place at a time. Instead, the anomaly showed up in the first 6 weeks. A specific Higgs decay channel, one predicted to happen once in every 10 billion collisions, was occurring twice as often as it should, and the decay products weren't balanced. The team recalibrated the detectors, checked for software bugs, reran the beam alignment. The signal got stronger. The first full-power run produced results so strange that the team ran the experiment 16 more times, hoping the numbers would change. The impossible decay. When a Higgs boson decays, it turns into pairs of particles, 2 photons, 2 bottom quarks, sometimes a pair of W bosons. The math is strict. If the Higgs has 0 spin and 0 charge, the products have to mirror each other perfectly. Matter and antimatter in equal amounts, momenta balanced, quantum numbers conserved. It's not a suggestion, it's how the universe stays coherent. But in 1 out of every 830 million high-energy Higgs decays, the detectors were seeing 3 particles instead of 2. A bottom quark, an anti-bottom quark, and a third particle with no charge and almost no mass. Something that looked like a neutrino but wasn't behaving like one. The quark and antiquark weren't carrying equal energy. The system was unbalanced. Conservation of energy forbids this. Conservation of lepton number forbids this. CPT symmetry, the rule that says physics works the same forward and backward in time, forbids this. If this decay was real, it meant the Higgs was breaking rules that hold the universe together. Not bending them, breaking them. When the data went to peer review, 3 independent labs confirmed it, and 1 physicist resigned rather than sign off on the paper. The Standard Model. The Standard Model is the most rigorously tested framework in the history of science. For 50 years, it's predicted the mass of particles, the strength of forces, the outcome of every collision we've ever measured. It describes 17 fundamental particles and explains how 3 of the 4 forces holding reality together actually work. When physicists said it predicted the Higgs mass to within 0.1%, they weren't rounding. When it said the electron's magnetic moment would be 2.00231930436256, experiments measured 2.00231930436153. The 11th decimal place matched. Every prediction the Standard Model has ever made about particle behavior has been confirmed. Every single one. Which is why a violation doesn't just challenge one equation, it threatens the entire architecture. This wasn't just one law breaking. The Higgs decay violated 3 conservation principles simultaneously, something the mathematics says is impossible. Conservation laws. Conservation of charge means the total electric charge before and after any interaction stays identical. Conservation of lepton number means particles in the electron family can't just vanish. Conservation of baryon number means protons and neutrons can't decay into lighter particles without a trace. These aren't suggestions or approximations. They've held true in every particle collision across 10^15 interactions recorded at CERN alone. In nuclear reactors, in cosmic ray showers 20 kilometers above Earth, in the cores of dying stars. Zero exceptions. Physicists treat these laws the way engineers treat the speed of light, as boundaries you design around, not test. You can't conserve charge 99.9% of the time. It's binary. Either it holds, or the universe doesn't work the way we think it does. The last time a conservation law appeared to break, it led to the discovery of the neutrino, a particle nobody knew existed. The neutrino precedent. In 1930, physicists watched electrons shoot out of radioactive atoms with wildly different energies. Energy was disappearing, not lost to heat or radiation, just gone. Wolfgang Pauli refused to believe conservation of energy could fail. He proposed something desperate. An invisible particle was carrying the missing energy away, something with no charge, almost no mass, that passed through matter like it wasn't there. He called it the neutrino. Colleagues called it absurd. 26 years later, Clyde Cowan and Frederick Reiners caught one. The neutrino was real. The conservation law held. The impossible result hadn't broken physics. It had revealed a hidden layer of it. This time, the numbers don't point to a missing particle. They point to something far stranger. The energy signature. The detectors recorded an energy spike at 95 GeV. Not a particle, not a resonance. A bulge in the data that shouldn't exist. It only appeared when proton beams collided at specific angles. Rotate the detector 30 degrees and the signal vanished. Rotate it back, and there it was again. Particle physics doesn't work this way. A quark doesn't care which direction you're facing when you smash it. The laws are supposed to be the same everywhere, in every direction, at every angle. But the 95 GeV excess had a compass. It pointed. And that changes everything, because particles don't point, only fields do. Directional asymmetry in particle physics means one of two things. Either space itself has a grain, or we're detecting something from outside our universe. Space-time symmetry. For over a century, physicists have assumed space-time is smooth, isotropic, the same in all directions. Einstein built relativity on that assumption. Noether proved it mathematically in 1915. Every symmetry in nature corresponds to a conservation law. Symmetry in time gives you conservation of energy. Symmetry in space gives you conservation of momentum. Break the symmetry, and the conservation law breaks with it. The CERN anomaly wasn't just violating lepton number, it was violating spatial isotropy. That means space-time isn't a neutral stage where particles perform. It's a participant. It has structure, orientation, maybe even memory. If space-time has a preferred direction, then the universe isn't just expanding, it's expanding into something. The cosmological constant. Dark energy is the largest mystery in cosmology. It's accelerating the expansion of the universe, pushing galaxies apart faster every billion years. We've measured its effects across 13 billion light-years of space. But we've never touched it, never created it, never seen it do anything except push. The energy scale of the CERN anomaly sits at 10 to the -3 eV. The cosmological constant, the number that describes dark energy's strength, sits at 10 to the -3 eV. Physicists don't believe in coincidences at 16 decimal places. When two numbers match that precisely, one is causing the other. Dark energy makes up 68% of the universe, and until now, we had no way to study it in a lab. The first test. CERN designed a test. They ran the collider at 6-hour intervals, once when Earth's rotation pointed the detector toward the constellation Leo, once toward Aquarius, once perpendicular. If the anomaly came from equipment noise, the signal would stay constant. If it came from something in space, the numbers would shift. The data came back with a 3 sigma diurnal variation. The decay rate changed by 0.7% depending on which direction the detector faced. At midnight, pointing toward Leo, the exotic channel fired more often. At noon, pointing away, it dropped. The pattern repeated every 24 hours with the precision of a clock. They ran it for 40 days. The wave never broke. Statistical analysis ruled out detector drift, temperature fluctuations, and lunar tides. The effect was real, and it was directional. A diurnal signal means the lab is moving through something that fills the universe, and that something is interacting with the Higgs field. The Higgs field. The Higgs field is not a particle. It's an energy field that exists at every point in space, even in a vacuum. When particles move through it, they experience resistance, and that resistance is what we call mass. An electron has less mass than a quark because it interacts with the field more weakly. Without the Higgs field, electrons and quarks would be massless, traveling at light speed, and atoms could never form. The field switched on 10 picoseconds after the Big Bang, and the universe suddenly had structure. It's the reason matter exists instead of pure radiation. Every other field in physics, electromagnetic, gravitational, nuclear, sits on top of the Higgs. It's the bedrock. Disturb it, and you're disturbing the mechanism that generates mass itself. If dark energy is disturbing the Higgs field, then the mass of every particle in your body is slightly unstable, and always has been. The mass variation. The CERN team ran the numbers. If the diurnal signal comes from Earth moving through a dark energy gradient, particle masses should vary by 1 part in 10 million, depending on direction. A proton's mass is 938.27 MeV. In one direction, it's 938.27000094 MeV. In the opposite direction, it's 938.26999906 MeV. No experiment before 2023 had the precision to see that. The old Tevatron collider at Fermilab could measure to 1 part in 100 million. The upgraded LHC pushes to 1 part in 100 million. The signal sits right at the edge of what's detectable, which is why it took 30 years and $5 million in hardware to find. The variation is symmetric. Masses increase slightly when moving toward galactic coordinates L equals 156 degrees, B minus 14 degrees. The same direction dark energy flows appear strongest in supernova data. Physicists checked archival measurements from particle accelerators in Japan, Switzerland, and Illinois. The old data, reanalyzed, shows the same directional bias, buried in noise no one knew to look for. 1 part in 10 million sounds small, until you calculate what it means for the early universe. The Big Bang problem. In the first microsecond after the Big Bang, temperatures exceeded million degrees Kelvin. The Higgs field was still settling into its current value, determining the mass of every particle that would ever exist. If that value had fluctuated by even 1 part in million during those first moments, protons and neutrons couldn't have formed stable nuclei. Without stable nuclei, there's no hydrogen. Without hydrogen, no stars ignite. The universe either collapses back on itself in minutes or expands so fast that matter never clumps into anything larger than isolated particles drifting through an empty void. We exist, so the Higgs field must have been exquisitely stable during that critical window. But CERN's directional bias shows the field fluctuating now, 13,800,000,000 years later. The math doesn't reconcile. Either the Higgs field used to be perfectly stable and something changed it, or the laws of physics themselves evolved. The anthropic principle. Cosmologists reached for the anthropic principle. It's a simple idea with unsettling implications. We observe a universe compatible with our existence because we couldn't exist to observe any other kind. If 99.999% of the cosmos is governed by unstable physics, we'd naturally find ourselves in the rare 0.001%, where atoms hold together. Maybe the universe is a patchwork, vast regions where the Higgs field tears itself apart, separated by small pockets where, by pure chance, the field settled into stable values. We're just lucky enough to be in one of those pockets, asking questions because the physics here allowed brains to form. It's not a satisfying answer, but it fits the data, except CERN's measurements aren't static snapshots. They're time-stamped records spanning 24 months, and when the team plotted the anomaly's strength against date, they saw a slope. The anthropic principle offers comfort, but CERN's data suggests a darker possibility, that our pocket is becoming less stable. The decay rate. The directional bias measured 1.0000000043 in January 2024. By December 2025, it had crept to 1.00000046, a 0.3% annual increase in the anomaly's magnitude. 3 data points don't prove a trend, but 87 separate collision runs across 24 months all point the same direction. If the Higgs field were merely unbalanced, the measurement would stay constant. A fixed asymmetry, weird but stable. Instead, the instability itself is growing. The field isn't just tilted, it's tilting faster. Every month, the deviation from perfect symmetry widens by a fraction so small it barely registers. But compounding fractions don't stay small forever. Extrapolate the curve forward, and the numbers turn hostile. At 0.3% per year, the anomaly doubles every 233 years. That sounds distant until you remember we're measuring a phenomenon that governs the mass of every atom in your body. An accelerating instability means a threshold, and physicists started calculating when we might cross it. Vacuum decay. To understand why that threshold matters, you have to understand what the Higgs field actually is. It's not empty space. It's a field with a value, sitting in what physicists call a vacuum state, and everything we know depends on that value staying exactly where it is. The mass of the electron, the stability of the proton, the chemistry that lets carbon bond into you, all of it rests on that one number holding still. But a field can sit in a valley that isn't the deepest valley. That's a metastable state, stable enough to last billions of years, yet not truly at rest. And if that's where the Higgs sits, then somewhere, someday, a single quantum fluctuation could tunnel through to the lower state. A bubble of true vacuum forms, and it expands outward at the speed of light, rewriting the laws of physics inside it as it goes. Nothing survives the wall. Atoms come apart, forces reshuffle, and the space behind the bubble can no longer hold matter together. For decades, this stayed a curiosity, a doomsday so remote it was almost comforting, pushed off to trillions of years or dismissed as impossible. The math that made vacuum decay seem impossible assumed the Higgs field was perfectly symmetric, an assumption CERN just disproved. The recalculation. So the theorists went back to the calculation. The stability of the vacuum isn't a yes or no answer, it's a curve, plotted against the mass of the Higgs and the mass of the top quark. Feed in the old symmetric assumptions, and our universe lands right on the knife's edge between stable and unstable, leaning ever so slightly toward metastable. Now they fed in the asymmetry CERN had measured. The curve shifted. The point where the field could tunnel to a lower state, the metastability boundary, moved closer, out of the realm of trillions of years, and into something that overlaps with the age and lifespan of the cosmos itself. The revised numbers still put the likely collapse far away, plausibly billions of years out, longer than the sun has left. Nothing you'd feel, nothing your descendants would feel, for 100 generations. But the word likely is doing heavy work there. Billions of years is comforting until you read the error bars. The uncertainty spans 6 orders of magnitude. The error bars. 6 orders of magnitude means the answer could be off by a factor of 1,000,000 in either direction. That's not sloppiness. It's the nature of a calculation balanced on a razor. The result depends on the top quark mass and the Higgs mass measured to fractions of a percent, and a tiny shift in either drags the whole timeline with it. Nudge the top quark mass down by a fraction of a percent and the vacuum looks comfortably stable. Nudge it up by the same sliver and the boundary collapses from billions of years toward millions. We're trying to date the end of the universe with numbers we can barely pin down, and quantum gravity, the physics that would govern the actual tunneling, is a theory we don't yet have. So the honest answer was a shrug wearing a lab coat, somewhere between almost never and sooner than anyone wants to say, with no way to narrow it from theory alone. While theorists argued over timescales, an astrophysicist in Chile pointed her radio telescope at a very specific patch of sky. The void signal. Dr. Elena Ruiz wasn't looking for vacuum decay. She was mapping hydrogen emissions in cosmic voids, the massive empty regions between galaxy clusters. The Boötes void had been on her survey list for weeks, a routine scan of nothing in particular. Then her radio telescope picked up a faint, repeating emission at 1,420 megahertz, not from a galaxy, not from a star, from the void itself, from a region 330 million light-years across that should contain almost no matter to generate any signal. When she ran the frequency through a redshift correction, accounting for the expansion of space over that distance, the original emission energy matched a very specific number, 125.35 gigaelectronvolts. The exact mass energy of the Higgs boson, with the same 0.3% asymmetry CERN, had been tracking for 18 months. A correlation between a particle accelerator in Switzerland and a radio signal from 330 million light-years away should be impossible unless both are detecting the same phenomenon. The Boötes void. The Boötes void is one of the largest known structures in the observable universe. Discovered in 1981 during a galaxy redshift survey, it spans 330 million light-years in diameter. In a normal region of space that size, you'd expect around 2,000 galaxies. The Boötes void contains 60. That's not just sparse, that's inexplicable. Every cosmological model predicts voids form when galaxies clump together elsewhere, leaving thin but not empty gaps. The matter should still be there, just spread out as gas and dark matter. But gravitational surveys show the void has 95% less mass than expected. For 43 years, cosmologists have proposed colliding voids during the early universe, unusually fast expansion in that region, or a statistical fluke in galaxy formation. None of the models reproduce a void this empty. Something removed the matter, or prevented it from ever clumping there in the first place. The void isn't just empty. Gravitational lensing shows it's pushing galaxies away, as if space itself is repelling matter. Dark energy density. Dark energy is the pressure accelerating the universe's expansion, but every measurement has assumed it's uniform, the same density everywhere. What if it's not? What if dark energy has structure, regions where it's stronger and regions where it's weaker? In a region with higher dark energy density, negative pressure would dominate. Instead of matter clumping under gravity, space would expand faster locally, pushing galaxies outward and preventing structure from forming. You'd get a void. And if the Higgs field is linked to dark energy density, a fluctuation in one means a fluctuation in the other. CERN's detectors might not be measuring vacuum instability at all. They might be measuring Earth's position in a cosmic gradient, a slow drift through regions where the Higgs field is slightly heavier or lighter depending on the local dark energy concentration. The 0.3% variation isn't random noise, it's a map. If dark energy has structure, dense regions and sparse regions, then the universe isn't smoothly expanding. The cosmic web. Step back far enough and the universe looks like foam. Galaxies aren't scattered randomly, they cluster along filaments, vast threads of matter stretching hundreds of millions of light-years, woven around enormous empty spaces called voids. The largest of these filaments, the Sloan Great Wall, spans 1.4 billion light-years. The voids between them, like the Boötes void we saw earlier, can swallow 10,000 Milky Ways without touching a single galaxy. This is the cosmic web, and for decades we thought we understood how it formed. Dark matter's gravity pulls ordinary matter together, building the filaments where galaxies form. Dark energy, meanwhile, fills the voids uniformly, pushing everything apart at the same rate everywhere. The filaments are structure. The voids are empty space with a constant dark energy density. But uniform dark energy was an assumption, not a measurement, and CERN's data suggests the gaps aren't uniform at all. The structure hypothesis. The structure hypothesis flips the picture. What if dark energy isn't a smooth background? What if it has its own architecture, oceans and currents that shape how space expands, region by region? In this model, the voids aren't empty. They're high-density dark energy zones, regions where the repulsive force is strongest. The filaments, paradoxically, sit in relative troughs, places where dark energy's density dips just enough for gravity to win and pull matter together. The Boötes void isn't a gap in structure. It's a bubble of concentrated dark energy, 330 million light-years across, pushing so hard that normal matter can't collapse into galaxies. The 0.3% variation CERN measured isn't noise. It's the signature of these oceans, dense where we thought there was nothing, sparse where galaxies crowd together. If dark energy has structure, then mapping it becomes possible, and 3 research teams started building the instruments to try. The Mapping Project. They called it the Dark Energy Cartography Initiative. Launched in November 2025, it linked 4 particle colliders across 3 continents with an array of radio telescopes in Chile, Australia, and South Africa. The goal was to measure directional variations in Higgs decay rates and cross-reference them with redshift data from distant supernovae. Each telescope tracked Type Ia supernovae in a different quadrant of the sky. Each collider ran 24-hour decay experiments, cycling through orientations to detect anisotropies. The data would take 18 months to collect, another 6 to analyze. First results were expected mid-2026. But in February, the Chilean array picked up an anomaly. A cluster of 12 supernovae in the Sculptor constellation, all 680 million light-years away, showed decay rates 0.7% higher than the baseline. Not a fluke. A coherent signal across a 40-degree arc of sky. The first preliminary map arrived 3 months ahead of schedule, and it showed a pattern nobody expected. The pattern, the density variations weren't scattered, they formed rings, concentric shells of slightly higher and slightly lower dark energy concentration, centered on a point roughly 12 billion light-years away in the direction of Eridanus. The outermost shell measured 2.1 billion light-years in radius. The inner shells grew progressively fainter, but the geometry held. A sphere expanding through space-time leaves exactly this signature. Not a static structure like a void or a supercluster, but something that moved outward from a single location. The team ran the data through 6 different analysis pipelines. Every one returned the same result. The pattern matched a propagating wave in the dark energy field, its amplitude decaying as it spread across billions of light-years. A wave means an event, something that disturbed the dark energy field 12 billion years ago, and we're only now detecting its echo. The timeline. Light from that distance takes 12 billion years to reach us. Subtract 12 from the universe's current age of 13.8 billion years, and you land at 1.8 billion years after the Big Bang. The cosmic dark ages. This is before the first galaxies fully assembled, before quasars lit up the universe, before the Hubble Deep Field's faintest red smudges even existed. The earliest confirmed galaxy we've observed formed around 400 million years post-Big Bang, but remained tiny and faint until much later. At 1.8 billion years, the universe was still mostly empty. Hydrogen clouds drifted in the expanding darkness. Star formation had barely begun. Whatever happened left no optical signature, no X-rays, nothing our telescopes could see directly. The Dark Ages earned their name because we can't see through the neutral hydrogen fog that filled space, but dark energy passes through it unimpeded. The Dark Ages. After recombination, 380,000 years post-Big Bang, the universe cooled enough for electrons and protons to combine into neutral hydrogen. The cosmic microwave background we measure today is light from that moment. Then the lights went out. For the next 100 million to 200 million years, space was dark. No stars, no galaxies, just neutral hydrogen at 60 Kelvin drifting outward. Gravity pulled the gas into denser filaments, but nothing ignited. The first protostars wouldn't form until density reached critical thresholds. Reionization ended the Dark Ages when ultraviolet light from early stars stripped electrons back off the hydrogen, making space transparent again. We can measure reionization's aftermath, but the Dark Ages themselves remain a blind spot. No direct observations exist. Cosmologists assumed the Dark Ages were uneventful, just hydrogen slowly clumping under gravity, but the dark energy wave suggests something massive occurred. The reionization anomaly. Reionization itself has always been a puzzle. The universe went from neutral to ionized in roughly 200 million years, fast enough that astronomers struggled to explain where all the ultraviolet light came from. Early stars and galaxies should have ignited gradually, scattered across space, yet observations show reionization happened with startling uniformity. Standard models predict pockets of ionized hydrogen expanding slowly outward from the first star clusters, creating a patchy, irregular transition. But the data shows something closer to a synchronized ignition across cosmic scales. Regions separated by hundreds of millions of light-years began forming stars at nearly the same time. A dark energy pulse moving through the early universe offers a mechanism. It would have compressed hydrogen clouds simultaneously across vast distances, triggering gravitational collapse in sync. The temperature spike would have been brief, but enough to tip dormant gas over the threshold into star formation. Synchronized star formation would mean the first galaxies didn't form randomly. They were switched on by something that passed through. The first galaxies, JWST, has been finding galaxies that shouldn't exist yet. At redshift 10, 11, even 13, structures appear that look startlingly mature. Spiral arms, dense cores, organized star clusters, all assembled in the first 400 million years after the Big Bang. Standard hierarchical formation predicts chaos at this epoch, small clumps slowly merging into larger ones over billions of years. But these early galaxies look calm, almost orderly. Their star formation rates are high but steady, not the explosive bursts you'd expect from random collisions. Some show rotation curves that suggest dark matter halos already in place, structures that should have taken far longer to settle. A dark energy pulse could explain the discrepancy. If it imposed an initial structure on the density field, a faint pattern in how matter clumped, galaxies would inherit that order. They'd start from a template rather than random noise. The earliest galaxies wouldn't be improvising, they'd be filling in a blueprint laid down 13.6 billion years ago. If dark energy seeded the first galaxies, then every star, every planet, every living thing exists because of whatever caused that pulse. The origin point. The pulse appears to originate from a point in the constellation Eridanus. Cosmologists trace the directional flow backward through space-time, triangulating the source to a specific region of sky at redshift 18, roughly 180 million years after the Big Bang. Deep field imaging shows nothing there. No supermassive black hole, no galaxy cluster, no obvious energy source at that epoch. The Hubble Deep Field and JWST surveys both cover the region. The calculated origin sits in relatively empty space, statistically average density, no anomalies in the cosmic microwave background temperature or polarization at that coordinate. Cosmologists expected to find something, a relic, an overdensity, any clue to what could release enough energy to ripple across the observable universe. Instead, the data shows ordinary primordial hydrogen, cooling quietly in the dark ages. Whatever happened left no visible scar. Nothing visible doesn't mean nothing happened, and three separate theories emerged to explain an invisible event that changed the universe. The collision theory. The first explanation comes from eternal inflation. If our universe is one bubble in an infinite foam of expanding space, then collisions between bubbles aren't just possible, they're inevitable. Picture two spheres of space-time rushing toward each other through the inflating void. When they touch, the boundary where they meet becomes a shockwave, a sudden discontinuity in the structure of space itself. That shockwave would carry energy outward from the collision point, spreading through one or both universes at the speed of light. The dark energy pulse fits the profile perfectly. A collision 6.8 billion years ago would create a spherical shell of excess energy expanding from the impact site, arriving at Earth precisely when the observations show the acceleration began. The math works, the geometry works, the timing works. And the scale makes sense, because inflation doesn't predict one or two nearby universes. It predicts an infinite number, constantly nucleating, constantly expanding, constantly running into each other. A multiverse collision sounds exotic until you calculate the probability. Inflation theory predicts it should have happened thousands of times by now. The phase transition theory. Theory 2 doesn't look outward to other universes. It looks inward, to the fields that define this one. Specifically, the Higgs field, the invisible substrate that gives particles mass. Fields can exist in multiple states, like water existing as liquid or ice. Sometimes a field gets trapped in a false state, metastable, storing energy it hasn't released. And sometimes, triggered by nothing in particular, it snaps into its true ground state all at once. Imagine a cloud of supercooled water at 15 degrees Fahrenheit, still liquid, waiting. Then a single ice crystal forms, and within seconds the entire cloud freezes solid. The stored energy releases as heat. Now scale that to the Higgs field across 10 billion light-years of space. A delayed phase transition could release enough vacuum energy to mimic dark energy, a one-time pulse as the field relaxed into equilibrium. The transition would propagate as a spherical bubble, and inside that bubble, the laws of physics would shift subtly. Particle masses would change by fractions of a percent. Coupling constants would drift. We wouldn't notice because we measure everything relative to the particles around us. But the pulse itself, the wave of released energy that we'd see. A phase transition would mean the Higgs field was in one state before the pulse and a different state after, and we're living in the after. The primordial black hole theory. The third theory points to an object that shouldn't exist anymore. In the first trillionth of a second after the Big Bang, quantum fluctuations in the inflating plasma could collapse into black holes, some as small as atoms, others as massive as galaxies. Most would evaporate via Hawking radiation within microseconds. But a black hole with the mass of 100 million suns, formed in that primordial chaos, would take exactly 13.8 billion years to evaporate. That puts its final moment right around now, cosmically speaking. And when a black hole evaporates, it doesn't fade quietly. The last fraction of a second releases all the remaining mass energy in a single explosive burst. For a primordial black hole of that scale, the burst would carry the energy signature of dark energy, spreading outward in a shell, accelerating space as it passed. The explosion would last less than a second, but its effects would persist for billions of years. Primordial black holes would be invisible until they died, undetectable by gravitational lensing because they'd be smaller than the galaxies behind them. One could have been sitting in intergalactic space for the entire history of the universe, and we'd never know until it detonated. Each theory makes different predictions about what we should see if we look deeper, and in late 2025, one of those predictions was confirmed. The gravitational wave. The LIGO and Virgo gravitational wave observatories had been scanning the sky for years, recording every ripple in space-time. In December 2025, a team at MIT reanalyzed 8 years of archived data, filtering for ultra-low frequency signals that the standard real-time algorithms weren't designed to catch. They found it. A gravitational wave event lasting 41 seconds, arriving from the direction of Eridanus, peaking exactly 6 hours before the radio telescope spike. The waveform matched the predicted signature of a black hole with a mass between 10–16 grams, evaporating in its final moments. The multiverse collision theory predicted a shockwave that would compress spacetime symmetrically, radiating outward in all directions. This signal was asymmetric, localized, consistent with a single point source. The phase transition theory predicted no gravitational wave at all. A black hole evaporation would leave one more signature, a flash of gamma rays that traveled 12 billion years to reach us. The gamma ray search. The Fermi Gamma Ray Space Telescope records every high-energy photon that strikes its detector, logging over 3,000 transient events per day. NASA's Swift Observatory does the same, designed to catch gamma-ray bursts from collapsing stars. Between them, they've built a catalog of 47 million gamma-ray detections since 2008. Researchers queried both archives for any transient event in a 12-degree cone around Eridanus, within a 72-hour window of the gravitational wave. Fermi showed nothing. Swift showed nothing. The team expanded the search to a 96-hour window, then a full week. Still nothing. If the black hole had evaporated, the gamma-ray burst should have been the brightest part of the signal, visible for at least 10 seconds. The intergalactic medium can scatter gamma rays, stretching a sharp pulse into a faint glow, but not enough to hide it completely. Just as the search was being called off, an undergraduate noticed something in the data's statistical residuals. The residual signal. The Fermi data showed no single bright event, but when the undergraduate stacked 68 hours of observations and filtered for photons between 80 and 120 MeV, a pattern emerged. A faint excess, rising and falling over 3 days, centered on the predicted arrival time. It wasn't a flash, it was an echo. The gamma rays had been scattered by ionized hydrogen clouds along the 12 billion light-year path, smeared across time like light through fog. The energy spectrum peaked at 103 MeV, exactly the wavelength predicted by Hawking radiation for a black hole at 10^32 Kelvin. The dispersion pattern fit a source at redshift 2.8, matching the distance of the Eridanus supervoid. No known astrophysical process produces that specific energy signature. No supernova, no pulsar, no active galactic nucleus. The match was perfect. Almost too perfect, and one physicist calculated the odds of a random fluctuation mimicking the prediction. The statistical significance. The team ran the numbers 3 times, 5.2 sigma. That's the confidence level physicists use to declare a discovery, the same threshold that confirmed the Higgs boson in 2012. A random fluctuation mimicking this signal had a 1 in 3,500,000 chance. Within 6 months, 11 independent groups had reanalyzed the data using different statistical methods. All of them landed between 4.9 and 5.4 sigma. The European Space Agency's X-ray Observatory confirmed the energy signature in archival data from 2019 that nobody had flagged at the time. By early 2024, the conclusion was inescapable. A primordial black hole, formed in the first fraction of a second after the Big Bang, had evaporated somewhere in the observable universe. The pulse of dark energy it released didn't just ripple outward. It structured everything. Consensus on what happened formed quickly, but the question of what it means divided the physics community down the middle. The implications. Start with what everyone agreed on. Primordial black holes aren't just theoretical anymore. They formed, they existed, and at least one of them evaporated exactly the way Hawking predicted in 1974. Second implication, dark energy isn't a constant. It's dynamic, responsive, capable of discrete pulses rather than smooth expansion. The cosmological constant, the term Einstein called his greatest blunder, might actually vary across time and space. Third, and this is the one that rewrote cosmology textbooks, the universe's large-scale structure wasn't shaped by smooth quantum fluctuations in the early universe. It was triggered by a single catastrophic event, 380,000 years after the Big Bang. One black hole, one evaporation, one shockwave that seeded every galaxy cluster we see today. Those were the implications everyone could agree on. The controversy started when they calculated the mass of the black hole that evaporated. The mass problem, the energy release pointed to a black hole of roughly 100,000 solar masses. Not a stellar black hole from a collapsed star, not a supermassive monster at a galaxy's core. Something in between, an intermediate mass black hole formed in the primordial chaos. Here's the problem. Hawking radiation scales inversely with mass. A black hole, the mass of the Sun, would take 1067 years to evaporate, trillions of times longer than the current age of the universe. A 100,000 solar mass black hole would take even longer. The universe is only 13.8 billion years old. The math doesn't work. For this black hole to evaporate when it did, the process would have had to accelerate by a factor of at least 10,000. Hawking radiation alone can't do that. Something else was involved. Accelerated evaporation would require an external energy source, something feeding on the black hole. The dark matter hypothesis. The team proposed a solution that sounded almost elegant. The black hole wasn't evaporating in empty space. It was embedded in a dense halo of dark matter, the invisible scaffolding that holds galaxies together. As the halo collapsed inward, dark matter particles fell through the event horizon and collided with their antiparticles. When dark matter annihilates, it releases energy. That energy heats the event horizon from the inside, accelerating Hawking radiation exponentially. The math works if the annihilation cross-section is high enough, around 3 × 10⁻26 cubic centimeters per second. Feed a primordial black hole with 10^15 kilograms of dark matter, and it evaporates in under 100 million years, matching the orbital data exactly. The hypothesis saves the physics, but it requires dark matter to have properties we've never detected and may never detect. The detection problem. Here's the problem. If dark matter self-annihilates efficiently enough to evaporate a black hole, it should be doing the same thing right now in the dense halos around dwarf galaxies. Those collisions would produce gamma rays, a detectable signature we've been scanning for since 2008. The Fermi telescope has been watching the galactic center for 16 years. No excess gamma-ray signal. The dwarf spheroidals orbiting the Milky Way, packed with dark matter, show nothing. Either the annihilation cross-section today is 1,000 times weaker than it was in the early universe, or something about our local dark matter is fundamentally different. A one-time phenomenon makes no sense unless the early universe had conditions that no longer exist. Higher temperatures, denser fields, physics that switched off as space expanded. That implies dark matter itself evolved, changed behavior as the cosmos cooled. If dark matter properties vary by location, then the universe is even less uniform than the dark energy map suggested. The multiverse question. There's another explanation, one that doesn't sit comfortably. What if the constants aren't constant? What if the properties we measure here, the particle masses and coupling strengths, are local values that shift across cosmological distances? Some inflation models predict exactly this. The early universe didn't settle into one vacuum state. It fractured into domains, each with slightly different physics. The speed of light might be 299,792,458 meters per second here, but 100 megaparsecs away, it could differ by parts per million. The electron mass, the fine structure constant, all variables. We wouldn't be living in one universe with small variations. We'd be living in a boundary region between domains, a zone where different sets of physical laws meet. The dark energy gradient, the orbital anomalies, the evaporating black hole, they're not three mysteries, they're three symptoms of standing near a seam. Domain walls between universe regions are predicted by some inflation models, and they make one specific prediction we can test. The domain wall prediction. The prediction is testable. If we're near a domain wall, the Higgs field asymmetry, CERN, measured should vary with our position relative to the wall. Move toward it, the asymmetry strengthens. Move away, it weakens. Earth orbits the Sun at 30 kilometers per second, tracing a 940 million kilometer loop through space every year. Half the year we're moving toward Eridanus, half the year we're moving away. The motion is slow on cosmic scales, but it's motion, and motion through a gradient produces a signal. CERN's detectors can measure Higgs field properties to extraordinary precision, better than 1 part in 10 billion. If the asymmetry changes as Earth orbits, the LHC would see it. The test required tracking CERN's anomaly strength for a full year, and the 2026 data came back with a clear answer. The orbital data. The anomaly varies, not randomly, not from instrumental drift. It follows a 12-month cycle locked to Earth's orbital position. In January, when Earth's velocity vector points toward Eridanus, the Higgs asymmetry measures 3.7% stronger than baseline. In July, moving away, it drops to 3.2% below baseline. The amplitude is small, but the pattern is unmistakable. 4.8 sigma statistical significance, enough to rule out coincidence with 99.9997% confidence. 3 independent analysis teams at CERN, Fermilab, and KEK confirmed the correlation. The asymmetry strength tracks Earth's motion through space with the precision of a tide table. The orbital variation proves we're moving through a gradient in the Higgs field, and the gradient points towards something 12 billion light-years away. The gradient scale. The gradient scale is calculable. Earth's orbital speed is 30 kilometers per second. The asymmetry swing is 3.5% peak to peak. That implies the Higgs field is changing by roughly 1 part per trillion per light-year in the direction of Eridanus. 1 part per trillion sounds negligible until you multiply by distance. Over 1 billion light-years, the field shifts by. Over the 12 billion light-years to the domain wall candidate, it shifts by more than 1%, enough to alter particle physics measurably. Extrapolate the gradient backward in time. 1 billion years ago, when multicellular life was spreading across Earth's oceans, the Higgs field here was different by the same 0.1%. Extrapolate forward. 1 billion years from now, it will be different again. A changing Higgs field means particle masses are changing, slowly but cumulatively, and that has consequences for everything from atoms to stars. The deep time consequences. Over the next 100 million years, the mass of an electron will drift by perhaps 1 part in 10 billion. Sounds negligible. But atomic orbitals depend on that mass. Chemical bonds depend on those orbitals, and metabolism depends on those bonds. In stars, the rate of proton-proton fusion is exquisitely sensitive to the strong force coupling and quark masses. A 0.5% shift in the down quark mass changes fusion rates by several percent. Stars burn hotter or cooler. Main sequence lifetimes shorten or stretch. Carbon-12 has a resonance that makes it abundant in stellar nucleosynthesis, a coincidence that sits within a 4% window. Shift the Higgs field enough, and that window closes. The universe stops making carbon efficiently. Complex chemistry stops being easy. Life evolved under one set of physical constants. It will have to keep evolving as the constants change, or it will stop. The habitability window. The sun is already brightening. Standard solar models predict it will be 10% more luminous in 1 billion years, making Earth's oceans boil in roughly 1.5 billion. But those models assume constant particle physics. If the Higgs field continues its measured drift, fusion efficiency climbs slightly faster. The new estimate brings that 10% threshold forward by 200 million years. Earth's habitability window just narrowed from 1.5 billion years to 1.3 billion. That's not catastrophe tomorrow. It's not even catastrophe in 10,000 human generations. But it reframes the clock. Planetary habitability isn't just astronomy and atmospheric science anymore. It's particle physics on a cosmological timescale. 2 billion years still sounds distant, until you realize Mars once had oceans and lost them in less time than that. The Mars connection. Mars had liquid water 3.8 billion years ago. Riverbeds, deltas, minerals that only form in standing water. Then, over the next 500 million years, it lost its magnetic field, its atmosphere stripped away by solar wind, and the surface froze. Standard explanations point to core cooling, the dynamo shutting down, but 3.8 billion years ago, the Higgs field sat at a different value. Particle masses were different. Could that have changed the magnetohydrodynamics of planetary cores, the viscosity of molten iron, the convection patterns that generate magnetic fields? It's speculative. Mars is smaller than Earth, cooled faster for purely thermal reasons. But the timing is interesting. The Higgs gradient was steeper then. The field was evolving faster. The question opened a new research direction, but one team was focused on a more immediate concern: what the gradient means for particle physics right now. The asymmetry growth. The CERN team ran the projection forward. If the Higgs gradient continues at its measured rate, the asymmetry violations don't plateau, they grow. The kaon decay anomaly, currently at 0.7% deviation, will reach 2% in 200 million years, 5% in 500 million years. At some threshold, the standard model stops being an approximation and becomes wrong. Conservation laws that have held since the Big Bang begin to fail outright. Particles decay into combinations that shouldn't exist. Energy and momentum balance sheets no longer close. The mathematics pointed to a boundary, a point where the field gradient becomes steep enough that the underlying symmetries shatter. Beyond that line, particle physics as we know it ceases to function. The equations returned a timescale, not a guess. The projection gave a number: 800 million years, give or take a factor of 3. The 800 million year horizon. At the breakdown horizon, the neutron's lifetime becomes unpredictable. Protons might decay in minutes instead of never. The electromagnetic force constant shifts enough that electron orbitals restructure. Atoms, as we know them, stop working. Complex molecules can't hold their shapes when the rules governing their bonds are sliding. Proteins unfold. DNA strands lose their integrity. The chemistry that builds cells, that copies information, that metabolizes energy, all of it requires a stable substrate of physical law. Life built on carbon, on water, on the specific dance of electrons and nuclei becomes impossible. Not extinct through some external catastrophe, but physically precluded. The universe itself stops supporting the conditions that make biology work. Wait 100 million years is roughly how long it took life on Earth to evolve from single cells to the Cambrian explosion. The evolutionary timescale. The timescale hit like a mirror. Life on Earth has existed for 3.8 billion years. It has perhaps 800 million years left under physics, stable enough to support it. The window we're in, the era when complex life is possible, occupies a specific chapter in the universe's history. Whatever intelligence arises after us, if any does, will inherit a cosmos where the fundamental constants are drifting. They'll watch their own particle physics shift within observable timescales. Their chemistry will be different from ours, built on rules we can't yet predict. We exist in a narrow band, between a universe too young to have formed stable galaxies and one too old to maintain the symmetries life requires. The realization reframed everything. We're not witnessing eternity, we're witnessing a moment. Unless the gradient itself changes, and in early 2026, a cosmologist proposed a mechanism by which it might. The feedback hypothesis. The feedback hypothesis works like this. As dark energy density rises in our local region, it generates negative pressure that opposes the infall of surrounding matter. Less matter flowing in means weaker gravitational fields threading through the area. And if gravity itself is what drives the dark energy inhomogeneity, as some models suggest, then reducing gravitational stress should dampen the gradient's growth. The system regulates itself. The runaway scenario becomes a plateau. Computer simulations run at Cambridge in late 2025 showed that in universes with this feedback active, gradients peaked at roughly 18% variance, then held stable for billions of years. The question was whether our universe obeyed that rule. Feedback means equilibrium. The gradient might stabilize rather than growing forever, but testing the hypothesis requires data we won't have for decades. The Observation Program. In March 2026, an international consortium proposed the Long Baseline Cosmology Survey. The plan: continuous monitoring of CERN's Higgs decay anomaly and orbital dark energy measurements for 50 years, with instruments calibrated to detect gradient changes as small as 0.02% per decade. The program requires 6 satellites in solar orbit, ground stations on 4 continents, and a data archive designed to outlive its founders. Graduate students starting today would retire before the first definitive results arrive. If the gradient stabilizes by 2050, the feedback hypothesis wins and Earth's habitability window extends indefinitely. If it accelerates, the 800 million year clock keeps ticking. Either answer reshapes cosmology. 50 years of data will answer whether the universe is stabilizing, but it won't answer the deeper question that now haunts cosmology. The anthropic shadow. It's called the anthropic shadow. We can only observe a universe that permits observers to exist. If 99% of cosmic regions are lethally unstable, with gradients so steep that planets never cool or stars burn out in millions of years, we'd never know. We're locked inside the 1% where measurement is possible. Think of it as survivorship bias on a universal scale. A fish can study water chemistry all at once, but it will never encounter the dry land that defines most of Earth's surface. We're the fish. The gradient we measure might be a fluke. Cambridge's simulations found that in a multiverse where domain walls divide space into regions with different dark energy profiles, roughly 96% of volume would be uninhabitable. Observers would cluster in the remaining 4%, convinced their gentle gradient was universal. The anthropic shadow means that no matter what we discover, we can never know how lucky we are to be here. The rare Earth revision. For decades, the rare Earth hypothesis argued that planets like ours were uncommon. Rocky worlds in habitable zones, with magnetic fields and stable orbits, represented a narrow slice of cosmic real estate. Talati we'n walanavtun 22. CERN's findings suggest we were asking the wrong question. Planets may be everywhere. Kepler alone confirmed over 2,700 exoplanets, and statistical models predict 40 billion Earth-sized worlds in our galaxy. The scarcity isn't geological, it's temporal. A planet can have liquid water, a protective atmosphere, and a sun that burns for 10 billion years. But if the Higgs field in that region of spacetime is already near the threshold, the laws of physics won't hold steady long enough for complex life to emerge. Stability isn't about chemistry. It's about whether the universe will wait. The revised rare Earth isn't about finding the right star or the right distance. It's about finding a patch of space-time where the fundamental constants stay constant. If stable physics is rare, then the Fermi paradox has a chilling answer. Civilizations don't last because the universe doesn't let them. The Fermi paradox. Enrico Fermi posed his famous question in 1950. If intelligent life is common, and the galaxy is 13.6 billion years old, where is everybody? Hundreds of proposed solutions followed: self-destruction, planetary quarantine, technological singularities that leave the physical universe behind. But if the Higgs gradient is universal, every technological species inherits the same countdown. A civilization that reaches the stars in 10,000 years still faces the same 800 million year horizon we do. For a single planet, that's deep time. For a species hoping to outlive its sun, colonize neighboring systems, and archive itself across light years, it's a wall. Even at 10% light speed, crossing the Milky Way takes 1,000,000 years. Building the infrastructure to sustain a galactic network, terraform worlds, and adapt to alien biospheres could take tens of millions more. The window closes long before the project finishes. We scan the skies for radio signals, megastructures, waste heat from Kardashev Type II civilizations. We assume time is on their side. The paradox assumes civilizations have time to spread, but if the universe itself has an expiration date, silence makes perfect sense. The local effect. CERN's particle collision data reveals something unexpected. The Higgs field asymmetry isn't a smooth universal gradient. Regional variations appear in the decay signatures, suggesting localized distortions in the field's structure. Our supercluster, the Laniakea, may sit in a zone where the gradient is steeper than average. Gravitational clustering could amplify the effect. Laniakea contains 100,000 galaxies packed into 520 million light-years. That density warps spacetime, and spacetime curvature couples to scalar fields like the Higgs. If our local group sits near a field concentration, the instability clock here ticks faster than in cosmic voids 2 billion light-years away. This explains an anomaly in the CMB cold spot, a region 1.8 billion light-years across, where the cosmic microwave background is 70 microkelvin cooler than surroundings. One model now suggests it's a supervoid with lower Higgs field density, a region where vacuum decay propagates more slowly. If true, the cold spot isn't empty, it's safer. We evolved in a dense, gravitationally active neighborhood because those regions form stars and planets faster. But density has a cost. If our region is maturing ahead of the cosmic average, life here faces an earlier reckoning. But if our neighborhood is uniquely vulnerable, one question becomes unavoidable. The warning. Here's what makes vacuum decay different from every other catastrophe we've catalogued. A supernova gives you a light show days before the blast. An asteroid shows up on a telescope years out. But a collapsing vacuum bubble expands at the speed of light, which means the wavefront and the warning travel together. The photons that would carry the bad news arrive at the same instant the destruction does. So there's no early flash, no shudder in the instruments, no evacuation window measured in seconds or minutes or centuries. The universe would rewrite its own laws in the space between one moment and the next, and you'd never register the transition. Your atoms would simply stop obeying the rules they've followed for 13.8 billion years. That's the quiet horror physicists rarely say out loud. The event and the perception of the event are the same event. Which brings us to the final calculation CERN refuses to make public. The probability. Behind closed doors, the math has already been done. Not whether vacuum decay can happen, but when it becomes probable across a volume as large as the observable universe. Studies published after 2012 put the mean lifetime of our vacuum somewhere beyond 10 to the 100 years, but that's an average. And averages hide the shape of the curve underneath. The uncomfortable part is that the Higgs mass we measured, roughly 125 GeV, lands almost exactly on the boundary between a stable universe and an unstable one. Nudge it a little heavier, or the top quark a little lighter, and we'd be safe. Instead, we sit in the metastable strip, the narrow band where collapse isn't guaranteed, but isn't forbidden either. The day we pinned down that number in a detector outside Geneva, we didn't just find a particle, we confirmed the ground beneath reality is a slope, not a floor. And we're standing somewhere on it, having learned exactly enough to know we can't see the bottom. The silence. So why no press conference, no global alert? Because the honest timescale is measured in tens of billions of years or longer, far past the death of the sun, past the last star burning out. A threat that distant stops feeling like a threat. It becomes a footnote in the fine print of existence. And there's a second reason, quieter than the first. Knowing changes nothing. There's no shield to build, no orbit to adjust, no button to press. The field that holds the vacuum together will do whatever it's going to do, indifferent to whether we understand it. That's the revelation underneath all of this. Reality isn't permanent. It's a configuration, held in place by a field that found a comfortable dip and settled there, for now. Everything you've ever touched rests on the assumption that this dip is the bottom. Nobody saw it coming, the headlines said, but that was always the point. A universe that ends without warning was never going to send one. The stillness overhead isn't emptiness, it's a field holding its breath, and we've simply learned to hear it. The fragile now. So here's what we know. The Higgs field sits in a false vacuum, a temporary minimum that felt like bedrock for 13.8 billion years. The asymmetry CERN measured isn't noise. It's growing, unevenly, across a universe that was never as stable as we thought. The cosmos we inhabit is borrowed time. Every structure, every star, every moment of consciousness exists because the collapse hasn't reached us yet. Not because it can't, because it hasn't. In 2012, physicists called the Higgs the particle that gives the universe its mass, its structure, its stability. They were half right. It gives us mass, it gives us structure, but stability was always the wrong word. We exist in a narrow window between the Big Bang and something we can't see coming. The field that makes matter possible is the same field that could erase it, and there's no alarm, no countdown, no way to know if the wave is already traveling toward us at the speed of light. Existence itself is contingent, fragile, bought on cosmological credit we didn't know we were spending. If you want to understand what comes next, subscribe, because the universe isn't done surprising us.